I realize by now you probably have this burning question. Is there a quick way to calculate the magnitude of the cross product? Let me answer that for you. It will be quick, but to get that quick shortcut, we're going to have to take the long way to get there. First, I want us to remember that the cross product follows this equation. If we look at the cross product between u and v, we use all of the components of u, we use all of the components of v, and we plug them into this expression. So then if we were to do the magnitude squared of the cross product of u and v, then we would take that vector, u cross v, each of the components would then be squared. So we've got the x component shows up here, squared. Same with the y component, same with the z component. If we multiply all of these out, remember that they're going to follow the perfect square binomial pattern. So this first one, for example, we'll multiply that one out just to show how it goes. That would look like u2 v3 minus u3 v2 times that same thing. And we would FOIL it out. So we'd have to multiply the first two terms. That would look like u2 times v3 squared. Then we'd multiply the second group. That would look like minus u2 v3 v2. Then we'd multiply our insides. That would be minus u3 v2 u2 v3, and then our last terms. So we're just using FOIL here. That would be 2 quantity squared. And the middle terms, although they look slightly different, they're actually all the same factors. I have a u2, I have a v3, I have a u3, and I have a u2. So even though they're in different orders, they are the same products. So I can group them together and say that I have two of them. And I'm just picking the order from that first version arbitrarily. It doesn't matter which one you keep. Okay, we're going to do this for each of these perfect square binomials, but I'm not going to write it all out. So if you can follow this, then you could easily calculate the next two to see that we get the following relationship. So multiplying out our first group of terms, we see the result here. Multiplying out our second group of terms, we see that result here. And then our last group of terms, we see that result here. Oops, I underlined too much over here. I really like green, so I guess I took it too far. Okay, now that we've multiplied all of these out, we're going to apply some dirty math tricks. This is everybody's favorite part of math class, dirty math tricks. What we're going to do is add and subtract identical terms, and we're going to pick special terms to make this equation factorable. The pattern that we have in mind is what we have here on the screen. And notice that in the factored form, we have the product of what almost looks like the magnitude of a vector squared, or a vector dotted with itself, times another one. What we actually are going to try and mimic is the right side of this equation. What I mean is, take a look here. We already have some of these terms. These are all terms that appear in the multiplied out version of that factored expression that we're going for. So let's think about which ones are missing. I don't see u1 squared v1 squared, so that's one of the terms that we need to add and subtract. I do see a u1 squared v2 squared. That's right here. So we already have that. I'm going to cross it off. u1 squared v3 squared. We have that here. So I'll cross that one off. u2 v1. That's over here. Oh, I'm crossing them off down here. u2 squared v2 squared. I don't see that one. So we need that one. u2 squared v3 squared. That's our first one up here, so I'll cross that off. We already have it. u3 squared v1 squared. That's right here, so I'm going to cross that off. We have that. u3 squared v2 squared. That's right here, so I'm going to cross that one off. And then u3 squared v3 squared. I also don't see that. So the 6 terms that we already have, I've crossed those off. And I've underlined the 3 that we're missing. So if we add those 3 to our equation, then we'll have all the terms we need to write this factored form. So let's go ahead and do that. If we add and subtract those terms, notice I've added the u1 squared v1 squared, the u2 squared v2 squared. Oops, that's not the right one. That is. And then the u3 squared v3 squared. But I've also subtracted those same terms over here. So the minus sign is outside the parentheses, meaning I'm subtracting each one of these 3. So it's like I didn't do anything to my equation because I added and subtracted the same term like it was never even there. That allows us to factor all of those terms in the front using the pattern that we identified. And then we have this stuff left over in the back. If we move some of the factors around in these last terms, it might be easier for us to see a pattern that's appearing. So what I'd like to do is I see u1 and v1. I see u2 and v2. So let's write them in corresponding orders. So now I'm going to do u1 v1, u2 v2 for that first term, just reordering the factors, and I'll do that for the other 2 as well, so that the numbers are matching up. The reason I want to do that is because we can see that that last group of terms factors nicely too. It's actually another perfect square type scenario. It's a perfect square trinomial. We have 3 terms here. And if you don't believe me, multiply this out and you'll see that you have exactly what's going on in the line above it. So this term is the factored form of the last term in the line above it. I'd like to say that we're almost done, but we actually just ran out of room on this slide, so we're going to continue on a new slide. Keeping going. So here's where we left off. The last term that I see in the parentheses, so let's zoom in here, u1 times v1, u2 times v2, u3 times v3, all added together. That looks a lot like a dot product. So let's replace it with a dot product, u dot v. And we have another way to write the dot product. U dot v can also be written as magnitude u times magnitude v times cosine theta. So let's make that replacement. Instead of u dot v, we now have this version of the dot product in our equation. And we're going to multiply out that last term, basically just distributing this exponent. And I'm also looking at these first 2 factors and thinking we can write those in vector form. So this looks like the vector u, whose magnitude has been squared, and this one looks like the vector v, whose magnitude has been squared. So let's go ahead and replace those terms, simplifying it for us. And now I can see that I have 2 terms, term 1, term 2, and the 2 terms have a common factor, so I'm going to factor that out so that I have the magnitude of u squared, the magnitude of v squared outside of the parentheses here, and then I have 1 minus cosine squared inside of the parentheses. So I just factored out that GCF to bring it out front. And now, looking at what's in the parentheses, I'm thinking of the Pythagorean identity. So let's go ahead and replace that with sine squared theta. And, well, there we go. We'll never have to do that again, but we have this beautiful shortcut that we can use to calculate the magnitude of a cross product quick. All we need is the magnitude of u, the magnitude of v, and the angle between them. In fact, we don't even have to calculate the cross product to find out what the magnitude of it would be. So this is great news. Now that we have this neat little trick for calculating the magnitude of a cross product, let's go ahead and calculate one. Now I've picked two vectors, u and v, that we should easily be able to see the angle between them. U is parallel to the j vector. Notice that there's a 0 in the x component, 0 in the k component, so u really looks like 4j. So it's like 4 of the j vectors. V is parallel to the k component, 0 in the x, 0 in the j, or y, and a 3 in the z, so we've got negative 3k. So if we're looking at the j vector and the k vector, we know the angle between these. It's 90 degrees. So theta is 90 degrees. This is a perfect case for us to use this shortcut. We can find the magnitude of u, we can find the magnitude of v. Both of those calculations are quick, and finding the angle between these isn't that bad either. So if we want to find the magnitude of our cross product of u crossed with v, we're going to take the magnitude of u. Well, I guess we need to calculate that then. That's going to look like 4 squared square rooted, which is just 4. And then we also need the magnitude of v, which looks like negative 3 squared square rooted, which is 3. So we'll do 4 for the magnitude of u times 3 for the magnitude of v times sine of the angle between them, which we said is 90 degrees. In other words, we have 12 sine 90. Sine at 90 degrees is equal to 1. So our final answer is 12 times 1, or just 12. So this cross product, the cross product of u and v, it creates a vector that's perpendicular to both of them. That vector, we don't know much about it, other than we know that it's 12 units long. In this case, because j and k are the vectors that make up u and v, we know that our cross product has to be pointing along the x-axis. And if we're going from u to v, then we're going from j to k, which means we're pointing along the positive x-axis. We could find that cross product. U cross v is going to be 12 I hat.